Great. Yeah, thank you very much for the introduction, Chairman, and thanks for the invitation for the organizers to come and talk to you guys today. And thanks for being accommodating. I was supposed to be here on Monday, and they graciously rescheduled me for Wednesday. Some of our recent work looking at this triangular lattice antiferromagnetic compound, sodium ruthenium O2. And I want to try and motivate why we think this compound is interesting, primarily from the fact that it's built from J-effective 1/2 spin orbit entangled moments on a triangular lattice, which is a reasonably rare material platform to find. And we originally started looking at it as a Heisenberg-Kitaev kind of candidate due to this geometry, which I'll explain in a bit. And then experimentally, it has sort of quite of an unusual disordered ground state, which I'll try and give you this sort of experimental diagnostics of that. And since this conference is on dynamics, I'll try and focus on a little bit on the slow dynamics in the system and try and what our current experimental pictures of those are. Okay, so first off, the people who did the work. So this project has been ongoing in my group for a while. A lot of it was just the materials development, trying to make the material in a pristine way. And this was led really by Brendan Ortiz and Paul Sart, two former postdocs in my group. Also joint with Alain Hendler-Avador, who's still a graduate student in my group. And we've had a lot of very fruitful collaborations. We've worked with Leon here quite a bit in trying to understand this material, as well as Ram Sastry in the materials department. And then a longtime collaborator of ours, Mike Graff, has done some very nice muon spin relaxation work, which I'll try and explain to you guys later in the talk. And then more recently, some theoretical, like ab initio type of modeling efforts by Rosa Valenti's group, and also Livio Hossoi's group at the IFW, doing quantum chemistry. Okay, so as I'm sure was covered a bit yesterday, the triangular, or 2 days ago, the triangular lattice antiferromagnet has a number of different mechanisms to try and create some type of intrinsically quantum disordered or quantum spin liquid ground state, which generally revolve around trying to either consider extended exchange mechanisms or anisotropy in the exchange of the system. And so once you start thinking about anisotropic exchange or bond-dependent exchange terms, then one can get a very complicated spin Hamiltonian in the parameter space of which can, in principle, in certain parameters, stabilize intrinsic kind of spin liquid states. So experimentally, in trying to make real materials that can host this, to try and kind of engineer this anisotropy, one approach is to take the magnetic moments that you're actually decorating the triangular lattice with, and then find the right parameters where you can basically use spin-orbit coupling to entangle the orbital and spin degrees of freedom. And there's really two sort of limits that we've been looking at over the years. One is where the spin-orbit coupling is really strong compared to the crystal electric field, and the other is where it's weak. And in this case, we'll be looking at the case where it's a spin-orbit coupling is weak compared to the crystal electric field, meaning we'll be looking at a low-spin ruthenium 3+ ion. Okay, so the idea for creating this spin-orbit entangled wave function is to start for something like ruthenium 3+. And this is a 4D electron with 5 electrons in it. So basically, if we look at the L shell, it's sort of half filled. But then you put it in a strong crystal field, so in the center of an oxygen octahedra. And in the low spin state, then you have a single hole in the T2G band. But since you still have this orbital degeneracy, then you can have spin-orbit coupling, which, if it's appreciable enough, can then split this T2G, these states that have L effective of 1, into lower J3 halves and upper J1 half band. And then you end up with a half-filled J1 half orbital, which is split away from the J3 halves by 3 lambda over 2, where lambda is the spin-orbit coupling constant. And then if you have appreciable Coulomb interactions still on site, then you can split this J1 half band into upper and lower Hubbard bands, and you have this sort of canonical J effective 1/2 Mach state. And so the wave function you end up with, as done by a lot of this, as we'll show a bit, mapped to materials by George Kelly and Ginyet Kalayuyan, is this the spin orbit entangled wave function with well-defined phases between the different orbitals. Okay. So this is of interest on lattices of edge-sharing octahedra because of mapping to sort of this model by Alexei Kitaev, where if one can envision having these bond-directional exchange terms, then on a honeycomb lattice, then one can have sort of exactly solvable quantum spin liquid state, which is often called sort of the Kitaev quantum spin liquid. And so George Kelly and co-authors basically mapped this sort of toy Hamiltonian into real materials via saying, okay, what if we have these J-effective 1/2 wave functions built from these 2G orbitals, and you decorate a honeycomb lattice with them? Then, in principle, you can have a regime where the Heisenberg exchange cancels, and you're left with these bond directional exchange terms that map sort of to the original ideas of Kitaev. Okay. So there's been a large effort in trying to find materials manifestations of this now that sort of the parameters were established. And I would say the two leading candidates historically have been an iridate, so sodium-2, iridium-03, or lithium-2, iridium-03, which is a honeycomb lattice of, in this case, it's iridium-4+, so this J-effective 1/2 moments that decorate the honeycomb lattice. And then the second is ruthenium trichloride, which is now the ruthenium regime, so spin-orbit coupling is a little weaker. But again, J-effective 1/2 Mott insulator on a honeycomb lattice. And so both systems have additional exchange terms, for instance, symmetric off-diagonal exchange terms, as well as finite Heisenberg coupling terms, because they're not exact kind of cubic crystal fields about the magnetic ions, that basically cause them to order below a certain temperature. So these systems, even though they're promising Kitaev magnets, they nevertheless order antiferromagnetically. So in the 213 or sodium-2 iridium-03, it orders below 18 Kelvin. In ruthenium trichloride, depending on the defects in the system, it orders below 7 Kelvin. But nevertheless, both systems seem to be close to the sort of Kitaev state, meaning they show signs of anisotropic spin fluctuations just above the critical temperature, for instance. Okay. So, and the reason that they order, as I mentioned, is that if you just think about, in this case, this is just considering the Heisenberg and Kitaev term. There's quite a spectrum of magnetic states that are predicted to be realized on the honeycomb lattice. But once you start mixing in a finite Heisenberg term, then you can see, as you move away from the pure kind of Kitaev or bond directional dependent exchange terms, then you can stabilize long-range magnetic order. So similar phase diagrams have been generated for a variety of different lattices that are built from edge-sharing octahedra, where in principle, you can also realize this cancellation of Heisenberg exchange and also this bond directional exchange term. And so for another example then would be the triangular lattice. And here's a theoretical phase diagram where this axis here is the Heisenberg axis and this is the Kitaev axis. And you can see in this particular work, there's predictions of a chiral spin liquid state. There are other works also mapping the triangular lattice where there's predictions of kind of this exotic kind of phase space of different magnetic states with these vortex crystals, pneumatic phase, and other kinds of strange ferromagnets. Okay, so this is sort of the starting point of why we were interested in looking at the triangular lattice. And also, from an experimentalist standpoint, the triangular lattice, is at least it's a 3-sublattice structure and it's sort of naturally frustrated. So if I start mixing in Heisenberg exchange terms, it's at least, okay, from a very hand-wavy perspective, at least the way we think about it when we're making materials, at least it doesn't want to order like the honeycomb lattice. Okay. Yeah.
What's the difference in the left and right picture?
This is a phase diagram for the honeycomb, and this is for a triangular. Yeah. Okay. And so this is where we got started looking for triangular lattice systems built from these J-effective 1/2 moments with the orbital wave functions being these 2-G states. And so this is how we focused in on sodium ruthenium O2. So what's the material itself? It's a layered system, so it's quasi-2-dimensionally, sort of chemically and magnetically. It was originally found by battery chemists. They like looking for these types of structures. So basically you have these planes of sodium that are separated by ruthenium oxide sheets. And then you have these ruthenium RuO6 octahedra that form this edge-sharing network. And so there's triangular lattice of ruthenium moments here. And they're about 3 angstroms apart. So when we started on the system, actually not much had been done. Like, is it a metal or is it an insulator experimentally? So we first had to do some things like this. So the first we just measure electroresistivity as a function of temperature. Indeed, it's an insulator, okay, which is a good starting point. If you want to say this is a J-effective 1/2 Mott state, it should have a charge gap. If you fit sort of the high temperature transport to some type of Arrhenius behavior for a hard gap, you get about 200 millivolts. That means the real gap's probably somewhat bigger, but this is sort of what we can parameterize right now with polycrystalline material. We can take it a bit further, and we can do X-ray absorption spectroscopy. And with that, you can look at the ruthenium L edges, the absorption edges in that system. And using sort of the sort of benchmarks that you can look at iridates and other ruthenates, then one can look at what's so-called the branching ratio across the ruthenium L3 and L2 edges, maybe for the experts. And from that, then you can basically determine if there's an orbital component to the ground state wave function. And indeed, the branching ratio for this is about 3, which is what you expect for a sort of a J effective 1/2 ground state wave function, okay?
Sorry, can you go back to the previous slide?
Yep.
The fits that are trying to make it seem like you want to fit into variable range hopping?
Yeah, so this fits best with variable range hopping, but if you want to just get some rough estimate of what the gap is in terms of the size, right? So we just fit the high temperature part here to an Arrhenius type behavior, and that will fit to sort of 200 millivolts. But if you want to fit the whole type of spectrum, then it's variable range hopping. Yeah.
Do you expect it's very disordered?
I mean, for a tunneling mode of transport? Yeah, I mean, well, I think in a lot of Mott systems, you end up with this variable range hopping type of transport. Like iridates, this is kind of commonly seen in a lot of these J-effective 1/2 Mott systems. Like strontium-2, iridium-04, strontium-3, iridium-207, these types of canonical J-effective 1/2 Mott states, they typically show variable range hopping transport. Okay. Any other questions on that? All right, good. So, what we want to do next is try and characterize the magnetic state. And so here one can do, this is just neutron diffraction. So basically you can take it from 300 Kelvin down to 1.5 Kelvin. There's no structural phase transitions, nor are there any magnetic phase transitions that one can see in neutron diffraction. One can go down to 50 millikelvin. And when you do that, basically you see no antiferromagnetic Bragg peaks pop up or no diffuse scattering that we can resolve within the resolution of the experiment coming from any magnetic short-range correlations. If one looks at the susceptibility as a function of temperature, it's a little odd. You have kind of this weak divergence in susceptibility, which I'll talk about a little bit more in a moment. It doesn't really fit well to any sort of Curie-Weiss behavior, and that could be due to a number of factors. One is that there's a reasonably large chi-naught term, which is likely due to the Van Vleck susceptibility of the system. That's also addressed with a weak impurity fraction, which we can fit to about 1% of spin 1/2 impurities in the system. And then if one zooms in at lower temperature, so this was, to 50 Kelvin, and then you kind of go to lower temperature, then you can actually fit the susceptibility to this kind of constant Van Vleck term plus an uncorrelated kind of impurity fraction of 1% spin 1/2 moment. So that can kind of capture most of this behavior, just to kind of parameterize the susceptibility for you guys. But if you go to lower temperature, so below 2 Kelvin, then you can see there's sort of this weak cusp. So this kind of a weak partial freezing somehow that's occurring around 1.8 Kelvin or so. And I'll be talking about that in a bit more. So basically, if you try and parameterize as a spin glass, this freezing, basically, you can look at the shift as a function of different frequencies of the AC susceptibility, then one can extract sort of this intermediate Majdash parameter. So it doesn't, okay, so that's parameterizing that. So one can say, okay, perhaps some fraction of these weak impurities are freezing as you cool down. As I'll show you in a bit, we think that's probably not the case via MUSR, but we'll talk about that in a second. If one looks at the heat capacity of the system then, so this is C over T as a function of temperature, and you cool down, then basically you see this kind of peak in the heat capacity around the same cusp that we see in the susceptibility in terms of the this weak freezing transition. And then if you apply a magnetic field, then you can see that this kind of gets shifted up in temperature and broadens out. So this is going from 0 Tesla to 14 Tesla in the red. And one thing to note is that if you look up to like 2 Kelvin here and you want to say what's the magnetic entropy encoded in this freezing here, it's actually fairly small, like maybe 1% of total, like R log 2. Okay, but nevertheless, one can try and parameterize this a bit more. So you can look above this freezing transition. So you can look up here, C over T versus T squared, and one can actually sort of extract a gamma-like term. So coming from low-frequency spin fluctuations in the system. And the gamma term is actually reasonably appreciable. So it's about 14 millijoules per mole per Kelvin, which is sort of the regime of metals. And if you want to, so obviously this breaks down when you approach this cusp at 2 Kelvin. And then, so to try and parameterize what the low temperature heat capacity is below this freezing transition, You can analyze the data where you put 14 Tesla field on, which you kind of push the cusp out of the way, and you can look at this low temperature regime. And in that regime, you can see that the heat capacity kind of conforms to this power law. Suppose it's about T squared down to 50 millikelvin. Okay, so there's a crossover in sort of the heat capacity as you go through this freezing transition, which kind of means it's sort of a global phenomenon, right? It's not just some 1% volume fraction. Okay, so then trying to analyze the spin fluctuations and how they evolve in the system, we can do inelastic neutron scattering measurements. And so this is sort of 3 windows of data for inelastic neutron scattering data, okay? And so they're coming in with 3 different incident energies, so you can view it as like different windows with different energy resolutions and different dynamic range. So, you have the energy transfer to the neutron as a function of momentum transfer. And so in this, you have the highest energy window. So this is looking at 80 millivolts. And as I'll show you in a moment, basically what this is probing is sort of this broad continuum of dynamics that extends up to about 30 millivolts or so. You can't see it so great on this projector, but you can kind of see that this sort of optical phonon mode that you can see at higher energies sort of gets enhanced in intensity because it's sitting on top of this continuum. If you zoom in a bit, so this is now coming in at incident energy of 42 millivolts, you can kind of see this broad continuum, and this is all coming out centered from a nuclear zone center for the system. And I'll show you some cuts parameterizing this in just a moment. And then you can come in at even lower energy, so now coming in with 3 millivolts, and so now our energy resolution is about 0.2 millielectron volts. And again, it's this broad continuum, and it's sort of gapless within our resolution of this measurement, okay? So within the inelastic neutron scattering measurements, basically you seem to have this sort of gapless continuum of excitations we parameterize roughly a 35 millivolt bandwidth. And this large bandwidth is what makes this experiment challenging, because you only have, in principle, J effective 1/2 moments, and all of that spectral weight is spread out over a really large dynamic range, instead of a lot of other, like lower J systems where you really compress it into a smaller phase space. Okay, but we can try and parameterize this a bit. So this is now taking an energy cut centered at a nuclear zone center, so along this axis for this higher incident energy data. And in this case, you can see here, so the key here is you just have this sort of broadish continuum with a kind of a peak here around 25 millivolts. This sort of, when you heat the system up, the excitations are still there, they just sort of broaden out a little bit. At lower frequencies then, this is this intermediate energy, you can cut across and just do a momentum cut, and you can see basically you have this broad continuum centered at the nuclear zone center for the system. Coming down at even lower energy, so this is the incident 3 millivolt data, then you can start to try and cut through excitations that are close to the gamma point, as well as excitations that are at this same nuclear zone center. And again, there's this broad kind of spectrum that comes up to about 3 millivolts. It seems to be gapless. There's no sign of like a peak here in the spectrum. But the odd thing about this is this is data collected at 250 millikelvin. So maybe this is maybe for people who are maybe used to looking at neutron data. This is the energy transfer of the neutron. So this is to the this is a neutron energy loss, and then this is neutron energy gain. And so on the neutron energy loss side, you can see here as you warm from 250 millikelvin to 12 Kelvin, there's really no change in this, okay? But if you look at the neutron energy gain side, you can see, this must follow detailed balance, okay? And so basically this gets populated up, which means that what we're sampling here is indeed excitations, but they're sort of, in this measurement, sort of temperature independent. And you can see the same when you do the analysis about the gamma point. Again, you have these, the spectrum of excitations that are sort of temperature independent on the neutron energy loss side, but on the energy gain side, they follow detailed balance. And so this sort of gives you hints that, since the neutron is sampling the dynamic structure factor, which can be related to the imaginary component of the dynamic spin susceptibility, just via this post factor here, then basically it kind of hints, often systems that show this type of behavior, that they will obey some type of scaling in the dynamic spin susceptibility as a function of energy over temperature. So indeed that happens in this system. And so it turns out that basically we don't have a ton of coverage, meaning we'd like to fill in this gap. We're trying to get data to do that. But nevertheless, you have the scaling collapse, meaning that the dynamic susceptibility ends up scaling as a function of E over T, which is kind of commonly seen in a lot of sort of quantum critical systems where you have spin dynamics that are originating from a quantum critical point, ranging from heavy fermion systems all the way to, this is potassium copper fluoride, sort of a 1D spin chain system. Okay, so that's sort of the neutron data. I'm just trying to be mindful of my time. Okay, and so looking at lower frequencies, this is muon spin relaxation data. So this is now trying to analyze the low frequency spin fluctuations in a bit more detail. And this is data that was collected by Mike Graff. And so anything I know about MuSR is from Mike Graff. So I'm going to do my best to explain this. All right. So this is the muon polarization as a function of time. And so what happens is you cool the system down. You have this really slow depolarization. But the moments, the electronic moments, eventually sort of freeze into the time window of the muons. And basically, you see this then rapid depolarization turn on as you cool the system down towards like 2 Kelvin here. Okay? So it turns out the form of this depolarization can't be fit to sort of the canonical paramagnetic moment model that a lot of muons use with the so-called Kubo-Toyabe function. Instead, it fits to this Gaussian broad and Gaussian Kubo-Toyabe function, which I'll show you in a bit, which is a model for highly disordered moments with an excess of low frequency fields. And then this Gaussian broad and Gaussian term is then further addressed by this slow spin fluctuation term here to fit the data. And the typical trick that you do with muons is that when you see a response like this, you want to see if this depolarization of the muon moment is being driven via static or dynamic processes. And so one way of doing that is you apply a longitudinal field to try and decouple the muon from the spin fluctuation background or the static spin disorder in the system. And so the benchmark is typically under very weak fields, you'll be able to rapidly decouple the muons from background static magnetic disorder, whereas dynamics will be much harder and require a higher threshold field to do. So in this case, the sodium ruthenium O2 system, applying up to 2000 Orsted, basically you still haven't fully lifted the depolarization process, which is consistent with like an intrinsically dynamic process disordering the moments in the system. And if one wanted to contrast with another frustrated spin system, so this is sodium 4 iridium 308, which is another J effective 1/2 Mott state, but in this case it's a 3-dimensional frustrated lattice, this like sort of hyper Kagame lattice. In this case, this system also depolarizes with this Gaussian broad and Gaussian term, but when you apply the longitudinal field in this system, basically they very rapidly decouple. And so this system is more consistent with static disorder, whereas the ruthenate seems to be driven more by fluctuating moments. And just sort of a touchstone, this Gaussian broad and Gaussian model is, I think, originally derived as an empirical way to capture depolarization in a lot of highly disordered magnetic systems. For instance, I think some of the original times it was deployed were for systems like yttrium-2, molybdenum-207, but also this the spin glass material cerium, copper-2, nickel-08 tin. And basically, the way you can differentiate it from the usual Kubo-Toyabe formalism is that you don't have this really deep minimum, you have this really shallow minimum, which in the model basically means that you have this excess of low field states seen by the muon. And it's seen in a number of unconventional frustrated compounds with kind of unusual glassy states in the ground state. So systems like ytterbium titanate, for instance. Okay. So another thing one can do is for the muon spin relaxation, basically what the muon can be, a quantity that you can map the local field of the muon seeing is to this autocorrelation function for the spins. And so some well-defined scaling relationships have been developed. For instance, for this field data, the muon polarization should scale as a function of time over the field to some power. And so the muon spin relaxation data that we have for the sodium ruthenium O2 system basically is consistent with an exponential, stretched exponential decay rather than a conventional power law or cutoff power law decay for conventional spin glasses. So it's just a sort of a further analysis of the low frequency muon data. Okay. How many? Oh, 5 minutes. Okay, I'm doing good. All right, I'll be done in 5. Okay, other things that we can do. Okay, so we can try and tune the chemistry of the system to perturb the magnetic state and see what happens. So this system actually lies on a going to expose you guys to some material space diagram, sorry here. It lies on this solid solution line between sodium 2, ruthenium O3, and sodium ruthenium O2. And so basically you can introduce a defect by taking an additional sodium ion and putting it on a ruthenium site. Okay? And so when one does that, you do something fairly dramatic to the system. You're basically introducing a non-magnetic impurity into the triangular lattice, but you're also tuning the spin-orbit coupling in that triangular lattice, and you're doping the system. Okay? So we can do that, and as soon as you start to tune the sodium content, you can see in the susceptibility, you immediately start inducing an irreversibility consistent with like a more conventional type of spin freezing in the material. So this is consistent with some degree of frustration that's being like lifted by adding some chemical perturbation. We can also then try the alternative. We can actually introduce a magnetic dopant or a magnetic impurity into the ruthenium lattice. So in this case, it's not a dopant. So this is basically putting iron 3+. And all this data is showing you here is that as soon as we put even just sort of 1% of iron onto the ruthenium lattice, we introduce irreversibility and susceptibility, again, consistent with inducing some type of local spin freezing. And once we can do that, as soon as we add a little bit of iron, we see the local moment coming from the local moments of the iron, and we can do a kind of Curie-Weiss type of analysis of the local moment in the system. And one of the oddities, if you look at the local moment in terms of the percentage of iron that we add to the system, we can extract what we think that the local moment should be relative to the full moment of the iron 3+ that we put chemically into the system. But the actual local moment that you get from the Curie-Weiss susceptibility is much larger. And so that's sort of consistent, basically these values end up mapping to a model where you have a local iron site that polarizes ruthenium moments, J effective 1/2 moments around it, and sort of slows them down, and we can start to sample them in the susceptibility. So this is kind of hearkening to some of the old models in like cuprates, where you can have these sort of local moment Swiss cheese models where you have impurities that sort of polarize the fluctuating moments around it. That's sort of our current picture, but we're still working on exploring this. Okay. And so finally, like trying to understand the models of interactions of this, there's been two really nice works that have been done. So the first is, this is by Rosa Valenti's group, where they did sort of a DFT approach, trying to understand what are all the allowed exchange terms from this exchange matrix. So you have, of course, the diagonal Heisenberg plus Kitaev exchange terms, and then off-diagonal so-called gamma and gamma prime terms, and they sort of calculate them to be the following. And so one of the interesting things about the system is that you actually get a fairly large antiferromagnetic Kitaev term that's predicted to form. But a dominant ferromagnetic J is predicted, as well as the largest energy scale are really these off-diagonal gamma terms. And so in this case, in this phase space that they calculated, the system should be a ferromagnet, which as an experimentalist is great because I know it's not that. Because short-range ferromagnetic order is not hard to find. Very weak short-range antiferromagnetic order is. But so we know that there's something else going on here, which is kind of strange. So similarly, this is Livia Hozoi's group doing quantum chemistry to try and analyze what the exchange term should be. And in this approach, again, an antiferromagnetic Kitaev term, as well as a dominant ferromagnetic exchange, as well as these gamma terms. But in this model, they also predict that it should be a ferromagnet. So in their work, they went a bit further, and they tried to analyze extended exchange terms, which, since it's a 4D transition metal ion, the orbital extent is larger, so you should have appreciable extended exchange effects. And so in this case, here's sort of the phase diagram they calculated. Well, there's maybe some very narrow sliver of a spin liquid state, but this is sort of ongoing, trying to understand what's the impact of extended exchange versus sort of these sort of anisotropic exchange terms. Okay, so good. And so to finalize, I had 1 minute. Okay, I'm just going to say that hopefully, there's a large number of classes of triangular lattice antiferromagnets where you basically use the spin orbit entanglement concept to decorate the triangular lattice, and you can destabilize long-range order. So there's been a lot of work done on like lanthanide systems, for instance, where you have these sort of S-effective 1/2 moments. But with going to higher energy scales and looking at like transition metal ions, so in particular J-effective 1/2 4D and 5D transition metals, you can generate a spin orbit Mott state where extended exchange effects and anisotropic exchange terms come into play. And they seem, in this case, it seems to sort of generate sort of a disordered state with some type of unconventional partial freezing at low temperature, despite the large energy scale for the spin dynamics in the system. And with that, I will thank you very much for your attention.
So all ab initio theories predict ferromagnetic interaction, and you're seeing antiferromagnet? Or?
Well, I'm seeing antiferromagnetism by virtue of the fact that there's no, we see no collective order, nor no ferromagnetism in the material, right? So, I mean, there's some data that goes up to sort of 50 Tesla. There's like no polarized. I mean, it's very,
and
very small.
Neutron scattering is not showing order down to very low temperature.
Neutron scattering doesn't show order, but the wave vector for neutrons is still Q is equal to 0. So that's, you know, that could be consistent with ferromagnetic fluctuations or, yeah.
Can you actually elaborate a little bit on the inelastic neutron scattering? The gapless excitations, they were at some...
Sure. Here.
Right.
Yeah.
Oh, so they're like exactly at adverse lattice constant. Is that like...
The Bragg peak.
Oh,
Yeah.
It's exactly at the Bragg peak.
Yes, yeah. It's very broad here. This is centered, but this is the Bragg peak, yeah.
And do you see any dispersion of those excitations, or?
No, this is like, it's powder data, so that's hard to assess. So there's a powder average here, so it's just more or less a continuum from our data set. We're still working on making high quality crystals. Yeah.
Is there hysteresis in the magnetization?
For the pristine material? Mm-hmm. No.
No. Also, could you show again the heat capacity as a function of temperature? So, like, what did you say the integrated up entropy was in the low temperature bit?
This,
yeah,
this is like maybe 1% of R log 2. And
how does that compare to like the fraction of spins that you saw freezing in the?
It's of the same order. Yeah, that's right. Yeah, but like, so one could say that, but then so potentially it's just coming from those spins just freezing, right? But then that would be sort of inconsistent with two things. One is that there's sort of this global change in the behavior of the heat capacity on the other side. And the other is that the muons are volume sensitive. You know, the muons see this depolarization happening at the same temperature scale, but it's coming from the entirety of the sample. Yeah.
Do you have any in-field data?
For neutrons?
Yeah, for neutrons or even specific heat in a magnetic field as a function of magnetic field.
Right. So in this heat capacity data here, this is the zero field data, and then as you apply a field, going up to 14 Tesla here, you can kind of see it get smeared out and pushed up. Mm-hmm. And this is sort of the highest field data we have for heat capacity. And so what you see then is this effective gamma term that we can extrapolate on the high temperature side of this freezing transition. Kind of has a field dependence to it. It goes up with magnetic field. It's a little weird.
And do you have magnetization up to these fields? How does magnetization behave? Is there some Laplace iteration, whatever? It's
basically just linear, yeah. I mean, there's a small cusp at very low field. I mean, like a small bend that one can fit again to sort of 1% of the total moments, maybe being paramagnetic impurities, right? If you fit, so you can do a Brillouin function for spin 1/2 for 1% volume, plus a linear term, which is just the antiferromagnetism going up. And so if the J is, you know, since the bandwidth is 35 millivolts, let's say the J is of the order of that, then we don't have fields to, you know.
So somewhat specific, it shows continuously changing power law. And it's
right.
Also probing like the low energy excitation, so that...
Yeah, right. So this, yeah, that's right. That's a good question. So how to interpret this is, I think, open, right? Because what the typical like experimental trick you would do would be, I'm just going to look at the highest field I have, and let's assume that pushes all of the kind of effects of this peak out far enough that I can actually access the really kind of intrinsic power law behavior. But But it does seem to continuously change, and if I could go like another 10 Tesla, ideally we'd want to see that this doesn't change as you keep going up higher. Yeah.
And if you do a log-log plot, does it look like a single power law, or maybe there's just, I don't know, maybe there's just some crossover you cannot see. I don't know.
I see. No, we haven't done that. Okay, that's worth it. Yeah, thank you.
Any other questions? Okay, so if not, let's thank the speaker again.